Okay, so we're almost done with the first half of this geometric optics topic. So we're almost done for the day. I'm going to just briefly remind you that we have convex mirrors that exist. And you may think that we're in for a whole new story for convex mirrors, but it turns out that we can pretty quickly find the image that's formed and the equation that relates focal length to the object and image distance. It's also valid just the same for convex mirrors. So I'll draw it out, but we won't address a full derivation because it's going to result in the exact same thing. So I'm just going to do a quick drawing to let you know what it in general looks like. We have the optical axis here. Center of curvature is now back here, C. We're going to have a point object here, P, and our vertex here, V. And we're going to consider two rays, one of them being this obvious one here. It goes out, comes back in. And I'm going to consider another one that goes out and hits somewhere towards the top of the convex mirror. And according to laws of reflection, it would then reflect off somewhere, probably something like that, right? Because whatever this normal is, this angle is going to be matched by, incident angle is going to be matched by the reflected angle. So what you then do is you would trace this back to find the image point. Trace this back. No actual light is coming here. And this guy is going to come back here, and you find that they intersect right there, right? And so that must be P prime, the image. And it's a virtual image, again, because there's no light actually intersecting back there. But if you were to draw more rays, right? More rays, then they would all, and down here as well, they would all act as if it was emanating from this point, similar to a plane mirror. And so that is definitely the virtual image back there. I'll let you, if you'd like, investigate what image is formed from an extended object and what that extended object virtual image looks like. Is it flipped? Is it magnified? What's going on with it? All right, so last thing I want to do is just summarize our graphing of principal rays. So I've been calling them example rays. We've had some practice now drawing these example rays, and it may seem like I'm just kind of picking and choosing whichever ones are convenient, and that's kind of how it goes. But there's a few guidelines to help you determine what image is formed and which rays would help you the most. So here I'm just going to summarize 4 rays that can usually be drawn to make this graphical determination, and these are called principal rays. Principal rays. So one of them is a ray parallel to the optical axis. Oops. And this one sometimes can just be implicit because it's just going to reflect right back usually. And then the second one is a ray through or in the direction of the focal point. A third one is a ray along the radius or in the direction of center of curvature, right? Because in this convex case, the radius is all on the right side, but there's no rays on the right side. So just in the direction of the center of curvature, which is the same thing as parallel to the optical axis for this point, but if you were to consider an extended object like this, right, a ray in the direction of the center of curvature is not the same thing. So that's why it's a separate ray. And then lastly, get back in there. Yeah, oops. Lastly, a ray to the vertex. right? So for a point object on the optical axis, a lot of these are exactly the same rays, but for an extended object, these all help. So these 4 principal rays can help you make a clear graphical determination of what kind of image is formed and where it's formed. It's important to remember that these aren't the only rays. It's really important to remember that. These are just the rays that are most helpful geometrically to make an image determination. But there are infinite rays radiating or reflecting from every point on an object going out in all directions. And that's why you can just pick a useful ray, because while they all exist, we just don't need to consider all of them. We're just considering the ones that are useful. So the last thing that I would like to do is I'm going to paste this over to where we are. I want to talk through some problem-solving strategy for these things, for the types of problems that you'll see involving object-image relations and focal point and all that. These little blue boxes in university physics are incredibly helpful for problem-solving and strategy and setting up problems. And they just, for a given class of problems, they usually have one of these blue boxes, and it helps you to figure out how to just approach the problem and set it up. And it works for all types in that class of problem. So first, for image formation by mirrors, right? Identify the relevant concepts. Problem-solving image formation by mirrors can be solved in 2 ways, using principal ray diagrams and using equations. A successful problem solution uses both approaches. Set up the problem. Identify the target variables. One of them is likely to be the focal length, or the object distance, or the image distance, with the other 2 quantities being given. And then execute it. So draw a nice large picture, and if you have enough information, and orient your diagram so that incoming rays go from left to right. Draw only the principal rays. Color code them if you find that to be helpful. I very much do. If possible, use graph paper or something else that will help you draw straight, clear lines. You may even want to use a ruler and really get into it and measure the distances carefully, but just keep in mind that if you get too loose with your sketches, it's not going to be very helpful. So if you're going with the graphical approach, you better go with the graphical approach all the way. If your principal rays don't converge at a real image point, you may have to extend them straight backward to locate a virtual image point. We saw a few examples of that. We recommend drawing extensions with broken lines to remind you that it's not real light that's going there, it's just virtual sources of an image. Measure the resulting diagram to obtain the magnitudes of the target variables. Or, if you're going with the equation approach, or if you're going with both, solve for the target variables using the equations that we wrote down. So 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. And the lateral magnification equation, which is that y prime over y, as appropriate. Apply the sign rules that we went over, the 3 sign rules, to object distance, image distance, and radius of curvature, and the object and image heights, which can tell you if the image is inverted or not. And use the sign rules to interpret the results that you deducted from your ray diagram and calculations. So it's the same sign rules that work for all 4 cases: reflection, refraction, plane, and spherical surfaces. Those sign rules we're going to carry through all the way through next lecture. And then, as always, evaluate your answer. Check the results of your calculations, agree with your ray diagram results and image position, make sure it all makes sense. Try to determine the image size and whether the image is real or virtual and what that all kind of physically looks like. Never just go ham on equations and then forget to evaluate afterwards whether your answer makes sense. All right, so hopefully that helps for figuring out what you need to with these problems. They shouldn't get too complex. I kind of went with the derivation approach for my lectures instead of just example after example of problems, so that leaves it to you with this full understanding of where these equations come from and hopefully a nice foundational understanding of geometric optics to now apply all this stuff and practice and practice and practice. Start with simple problems, work your way up. It's the same for all our topics, but I just want to make sure everybody has the correct approach for going through these lectures in this class and other future classes as well. All right, so that wraps it up for the day. This is a longer one. The next one is going to be also long because geometric optics is just like that.